Part 2 of section 16.8, we want to work an example problem now for Stokes' theorem. Let's look at number 3, where we are asked to use Stokes' theorem to evaluate the double integral over S of the curl of f dot ds where f is given by x squared z squared, y squared z squared, and xyz. And where S is the part of the paraboloid z equal to x squared plus y squared that lies inside the cylinder x squared plus y squared equals 4, oriented upward. Okay, so let's sketch this out. So let's start with the cylinder. That's kind of a boundary for us. If I kind of get that right. So the cylinder centered along the z-axis like that. We're working with the surface, which is the paraboloid. So the paraboloid, it's the part of the paraboloid that's inside the cylinder. So yes. So we're interested in that part of the paraboloid, which is inside the cylinder. And the orientation is upward, so n is not going to be a constant, but it does point, at least the particular value of n, which will be normal at the origin, that one will point directly upward. So in order to keep the surface S on the left, we would be moving across C here like this. And let's see, let's reread. So use Stokes' theorem to evaluate the integral of the curl along or throughout the surface S. Okay, well, we either do one of two things. We either evaluate the curl by evaluating the line integral, or we evaluate the curl by using the independence of surface result and then evaluating the curl along some or throughout this other surface. And because of the symmetry here, we can see this, the curve C is all at one height above the XY plane. We could figure out, well, that's easy enough. It's at the intersection of z equals x squared plus y squared and x squared plus y squared equals 4. So Z equals 4. So we could trade out this surface for the disk here. So let's do that. So let's use independence of surface and trade S for S prime. Let's see now. Be the disk. It's just going to be the disk x squared plus y squared equals 4, comma, z equals 4. The cylinder, I'm sorry, I mean, really, you could say x squared plus y squared less than or equal to 4. I wonder if I have that correct on my notes. I don't remember. Anyway, comma z equals 4. That would be the disk. So S prime. And the advantage to working with S prime is that we know that N now is equal to K. We know that it's K and not negative K because the original orientation was upward. Had they said the original orientation was downward, then we would be using negative K here. All right. So, of course, this is 0, 0, and 1. Now it's just a matter of going through and computing curl of F dot K ds. So what is the curl of F? Well, maybe I will allow you to double check this on your own, but I'll go ahead and give you the final answer here. The curl of this vector field is xz minus 2y squared z minus yz minus 2x squared z. Comma 0. And then, of course, we want curl of F dot K, and that's the dot product of these two vectors, and that's 0. So the whole thing just falls out. So the double integral over S of the curl of F dot ds is equal to the double integral over S prime of the curl of F dot S prime, which is equal to the double integral over S of 0 ds, which is 0. All right, well, this is sort of the ultimate, part of the material in this class, where when you get down to actually performing the computations, are, oh, the double integral of 0 is 0. The computations are a great big nothing burger, to use an idiom of the times. They're not overly long, but the challenging thing is to have your bearings, to understand what the theorem is and what it says. And of course, a big hint in section 16.8 homework is you're supposed to be using Stokes' theorem on the final exam, you may very well not be told which theorem you need to use. And so you would, again, you'd need to be able to see your way through the forest, understand the context. And then it's sort of the opposite, I always say, of calculus 1 and 2. In calculus 1 and 2, you have not overly complicated contexts with really long computations, and you have to really work hard at working an optimization or a related rates problem where you set it up and it's just kind of involved. Here, the the computations part is short and sweet, but you have to know what to do. So, all right, we will look at least one more example in the next lecture.